Next thing I want to talk about is when are you allowed to add different probabilities together and when you are not. And Theorem 9-3 states that the probability of an event is equal to the sum of the probabilities of disjoint events whose union is the event. And basically what this is saying is that if we're trying to figure out the probability of an event that is made up of multiple different conditions, we are allowed to add up those probabilities, assuming that they're disjoint. And by disjoint, all that means is that the sets don't have any overlap, so that when we're adding those probabilities together, we're not double counting anything. So let's look at an example. Number 4 says 3 coins are flipped. What is the probability that all heads are tossed? What about if all are tails? And then the last question it asks us is, what is the probability that all flips are the same? So again, we could start off by looking at, okay, what is our sample space? What is our event space for each of these examples? So let's just say that A1 is the sample space for this experiment, which is 3 coin tosses. So with 3 coin tosses, we could have the possibility that all of them are heads, which is one event. And another thing that's important is making sure that you get all of them. You could start off by making a tree diagram to represent all this, or we could use the fundamental counting principle. Since each coin flip is 2 outcomes and there are 3 flips, it'd be 2 times 2 times 2, or 2 to the 3rd power for the total number of elements in my sample set. So there should basically there should be 8 potential outcomes here. One is all heads, and how I like to find them all or write them all, often we would call them the permutations of those elements, is by fixing one and then rotating the other. So, if I started with heads, I'm just going to find all of the options that start with heads. So if I start with heads, I could also go, well, I could do heads, tails. I could do heads, tails, heads. And there's one other option. I could do heads, tails, tails. And that should be all of them that start with heads at least. And in the same sort of way, I could have started with the tails and had all the same outcomes from there. I could have tails, heads, heads, tails, heads, tails, 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 heads, and 3 tails in a row. And that gives me all 8 of the outcomes in my sample space. So the question, it asks, what's the probability that all heads are tossed? And that, I'll just call that A2. That's a pretty easy event. That's only one way of that happening. If literally all 3 are heads, that would be our event. And of course, we could also, the probability of that occurring based on our previous video, it should be the number of elements in our event divided by the number of events in our sample space. So probability that A2 is going to occur is going to be equal to, well, there's only one element in A2, and that would be divided by 8, the number of total events in the sample space. So we've got a 1/8 chance to throw 3 heads in a row. Or, if we prefer to rate that as a decimal or a percentage, we would have 0.125 or 12.5%. And similarly, the other thing it asks us is, well, what's the probability that they would all be tails? Sorry, I'm a little tired. I apologize if I slur my speech a little bit. But in the same sort of sense, there's only one way that this could happen. That's one outcome. So the probability that event A3 would happen is the same 1 out of 8, or 12.5%. So the question is, the third part says, what is the probability that all flips are the same? So, that event would be those 2 combined together. Or we might say it's the union of A2 and A3. The heads, 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 or tails, tails, tails. And obviously we could just do, we could use the original principle that it would be the total number of events 2 divided by the total number of outcomes 8. So the probability that either one of those could occur is 2 out of 8 or 1/4. But what we can see is that if we add those individual events together, the sum of those probabilities would be the combined. And again, since this is the union of those events, and since they're disjoint, again, which just means that they have no intersection, that they are unique, neither one has any overlap in their elements, that is what tells us that probability that A4 occurs is equal to the probability of A3 plus the probability of A2. Or, you know, it would just be 1/8 plus 1/8, 2/8, or 1/4, which is 25%. And, you know, that's the idea of adding probability. Again, which only can be, you're only allowed to add them like this when there is no overlap. If there is overlap, you need to make sure to take that into account. And let's look at one more example. This actually doesn't have to do with Theorem 9.3, but it says consider, but we will use it later. It says consider rolling 2 6-sided dice. Calculate the probability of rolling doubles. So doubles, you're probably familiar with the term, but basically it's kind of like the same, getting the same roll, like 2 1s, snake eyes, or 2 2s, 2 3s, and so forth. Very similar to, you know, this example where it's all the same outcome. So we could start with our event. Let's just call this E5 because I'm gonna use this in a later video. But this event would be, you know, if we get 1 1 on our dice, or 2 2, if both rolls come out 2s, both come out 3s, 4s, and so on, 5s or 6s. So of course there's 6 ways to get doubles with 6-sided dice, and so the probability of event 5 happening would be the number of ways it could happen, 6 divided by the total. And since the number of dice roll, we did this earlier, there were 36 total ways that you can roll 6 dice, or 6 squared. But that would give us 6 divided by 36, which is reducible by 6, would give us 1/6, which is 16.6% repeating. Because again, whenever that denominator has 3s in it, it will be a repeating digit. And yeah, that would be our probability for doubles here.